In single variable calculus, the derivative is the slope formula, essentially. And if the slope is positive, then the graph is going up. If the slope is negative, then the graph is going down. If the slope is zero, then maybe it's the top of a, maybe it's a maximum, top of a hill, or maybe it's a minimum. But we would take the derivative, set it equal to zero, solve for where those are to sort of figure out what the where the maxes and mins are, where the mins and max are, where the extreme points are. Optimizing functions, we had those word problems. How could we tell? I mean, if the slope was zero, how could we tell if it was the minimum or a maximum? Well, we looked at the second derivative. And if the second derivative was positive, it was concave up, so it's minimum. If the second derivative was negative, then it was concave down and it was a maximum. So the first derivative had to do with slopes, whether it was increasing or decreasing. The second derivative has to do with the concavity, if it's concave up or concave down. Now we're in multivariable. So we're talking about not just slopes in the x direction, but we'll have slopes in the, so here's y is running here from -3 to 3. So anything that we talk about here would be slopes in the y direction. If I look like this, now that's going to be slopes in the x direction. So we've got slopes in the x direction and slopes in the y direction. We also have second derivatives. So if I look at this, that looks like me doing this in single variable calculus, concave down, negative second derivative. So this has the x. I'm looking just on this level curve here, this slice. It looks like the second derivative with respect to x is negative, whereas over here, the second derivative with respect to x looks positive, looks like it's concave up. And here, now this is y in the direction of y, so we're treating x as a constant. The slope looks like it's going up, so the first derivative with respect to y looks positive. Here it looks concave down, here it looks concave up. So, talking about partial derivatives. First off, why are they called partial derivatives? Well, instead of just derivatives. Well, our function is a function of x and y. It's a multivariable function. So when I take the derivative, I'm looking at the slope, but I'm only taking the derivative with a part of the set of variables that I could take the derivative with respect to. So if I'm taking the derivative with respect to x, there's still a y, so that's why it's a partial derivative. So let's take a look at some notation. And I'm thinking about then the slope in the x direction. So for our curve here in the x direction, so I'm treating y as a constant. So here's our curve. If I'm taking the derivative with respect to x, I'm thinking about y as a constant. So let's narrow our viewpoint in then. If y is going to be a constant, let's not look at y from -3 to 3. Let's look at y from 2 to, let's say, 2.01. So that's a slice when y is equal to 2. So there's our curve when y is equal to 2. Looks like the slope is positive in the x direction. Looks like the partial derivative with respect to x will be positive over here, negative over here, and it looks like the second derivative with respect to x is going to be positive. But let's go back to our notation. We're talking about the slope in the x direction. So parallel to the x-axis, y is a constant. In our picture we made it 2, but it's a constant number. So notation-wise, we could do f sub x. So our function with the derivative with respect to x. So I'm differentiating with respect to x. All the other variables in this case there's only y, all the other variables, the y, is constant, are set as a constant. Now, why can't I just put f prime like we used to do? Well, there's some ambiguity there. If I say f prime, then you're going to ask me, is that the prime mean differentiate with respect to x, leave y constant, or does the prime mean differentiate with respect to y, leave x constant? The prime is ambiguous, it's vague. We can't use the prime anymore in multivariable calculus. So I need to use these, well, I like to use these subscripts. Another way of writing it is df dx, the change in the f as a function of the change in the x. Now, what's different about here, I'm using these funny d's. Why do I use the funny d's? Well, if I used regular d's, then I couldn't tell if it was df dx was a single variable function, derivative of a single variable function, or the derivative of a multivariable function. So the funny d's tell me that I'm differentiating with respect to x, but there were other choices. There must be other variables. So this is one way of writing the derivative, the partial derivative. Or I could do z sub x, or the derivative of z with respect to x. All of these things mean the same thing. It's the partial derivative with respect to x, the slope in the x direction with all the other variables constant. It's a measure of how much x goes up if I move over a little bit in the x direction. That's what the derivative means. Now, fundamentally then, here's our limit definition of the derivative. We had this in single variable calculus, f of x plus h minus f of x all divided by h. We take the limit as h goes to 0. We saw that before in single variable calculus. What we have now, though, is just keeping y as a constant. So I'm only taking the derivative with respect to x. So here it is as a limit definition. The y is a constant y. Another way of writing it, another notation, I don't use this, but you might see this in some books, is this means the derivative with respect to the first variable, the subscript 1, of the function. I don't use that notation, but you might see it someplace. Now, y is a constant. This next part that I'm going to say, this is all, in fact, literally copy-paste of this. But everywhere I said x before, I'm going to say y now. We're talking about the slope in the y direction, parallel to the y-axis. So it's f sub y, dy df, funny d's, z sub y. I'm taking the limit as h approaches 0. Here's our limit definition. But now it's y plus h and y. The x is the constant. Since y is our second variable, we could write it, I don't, but we could, as big D sub 2. Take the derivative with respect to the second variable of the function. X is a constant. So in our picture, we would see that as, okay, I'm zooming back, and now I'm going to zoom back in, but I'm going to make x a constant. Let's make it a constant of 1. So I'm going to look at 1 to 1.01. There's the curve when x is equal to 1, and I can see that the slope of this curve is the partial derivative with respect to y when x is equal to 1. Let's put it back. So I can see that when I take the, that was our curve when x was equal to 1, which is this line here. But you get different curves for different for different x values, but x is still a constant. So once we fix x, we're traveling in this direction. Formula-wise, then, so we're getting a different formula. Let's figure out how to get them. Actually, finding the partial derivatives is a pretty straightforward operation. It's just using all your regular differentiation rules that we learned in single variable calculus. But you're differentiating with respect to one variable and leaving the other ones as a constant. Example, here's our function, sine of xy plus x squared, 4y minus ln x, and we want to find the derivative with respect to x. So I'm going to call this the first order partial with respect to x. So I'm differentiating this function with respect to x, so y is a constant. So here I'm going to do chain rule. Derivative of the outside, derivative of sine is cosine, leave the middle alone, and now chain rule times by the derivative of what's inside. What's the derivative of xy? Y is a constant. If it was 7x, the derivative would be 7. It's not 7, it's y. 7 is a constant, y is a constant when we're differentiating. Now, the derivative of x squared, 2x. The derivative of 4y, 0, because y is a constant. So the derivative of a constant is 0. The derivative of ln x, 1 over x. So here's our first order partial. There's a formula that gives me the slope in the x direction at any xy point. If we want the other, I want the derivative with respect to y. So I'm doing the same thing. I'm differentiating with well, I'm doing the same thing, but I'm keeping the x constant, differentiating with respect to y. So chain rule again. The derivative of sine, cosine, leave the middle alone. The derivative of xy is now x, because that's the constant. The derivative of x squared, 0, because x is a constant, so x squared is a constant. The derivative of 4y, 4. I'm differentiating with respect to y. And ln of x, that's a constant, so its derivative is 0. So there's me differentiating. I've got the two first order partials, a slope formula in the x direction, a slope formula in the y direction. Let's do another example. We want the slope formula in the x direction. So I'm going to take the derivative with respect to x. So y is a constant. So y to the 5 is a constant. So this was just like as if this whole thing was 10. Just leave it alone. So that's going to be, when I differentiate with respect to x, 2x times y to the 5 plus 0, because that's a constant, minus the derivative of arctan x is 1 over 1 plus x squared. So I have to remember all my differentiating rules from single variable calculus. There's the slope formula in the x direction. Let's get our derivative with respect to y. So, differentiating, the x squared is now a constant. I'm differentiating with respect to y. So the 5 comes down, subtract 1 from the exponent. The derivative of 4y, 4. And arctan of x is a constant. So arctan of x is a constant. Its derivative is 0. Here's my two first order partials. Now we've done two examples. And these two examples make it look, pretty straightforward. Good. It should be pretty straightforward. The next example, the differentiating is just as straightforward, but it's just a notation. Notice that I get formula in here. Here I have a function, x squared plus 4xy minus y cubed, and we're asked for f of x evaluated at 0, 1. So the first thing I need to do is just get the derivative formula. So I'm taking the derivative with respect to x, so y is a constant. So that's going to be 2x plus 4 is a constant, y is a constant, derivative of that would just be 4y minus 0. So here's the slope formula. But I want it evaluated at 0, 1. So this, the derivative evaluated at a point, is a number. So make x equal to 0, make y equal to 1, and I get 4. What does that mean? That means at this surface, at the point 0, 1, what's the z value? Well, to figure out the z value, I'd have to plug 0, 1 into here. 0, 1 minus 1. When I plug x equal to 0 and y equal to 1 in here, I get minus 1. So at the point 0, 1 minus 1, the slope in the x direction is 4. So if I were to increase x a little bit, like go from 0, because it's at 0 now, 0 to, 0.001, then the z value would go up by about 0.004, because the slope is 4. All right, what about f sub y at 0, 1? Well, the process will be the same. I need first to get the derivative formula. So I'm differentiating this with respect to y. X is a constant. If x is a constant, then x squared is a constant. That'll be 4x. Nope, not there. Here. Minus 3y squared. And now I want the number when x is equal to 0 and y is equal to 1. That's minus 3. So the slope in the y direction is minus 3. So let's think about what we got here. We're at this point 0, 1, minus 1. If I move in the x direction, it goes up 4. If I move in the y direction, it goes down minus 3. So at this point, we can tell going this way up, going this way down. It's giving a kind of a tilt to the landscape. I wonder if we can see this if we graph this function. So it's x squared plus 4x minus x. So x squared plus 4x y minus y cubed. Okay, it's a continuous function. Make sure I typed it in correctly. I did. It's a continuous function, and we're interested at the point when x is equal to 0. So here in the middle, and y is equal to 1, so here. So we're about here, let's say. And if I go in the x direction, it looks like, let's set this up. So I'm back down here. If I go in the x direction, yeah, it's a slope of 4. If I go in the y direction, it's a negative slope. I'm at this point right there. So positive slope, negative slope. Just for some foreshadowing, it looks like right here in the sort of a middle of this, what looks like kind of a bent saddle, is the slope looks like it's 0 in the x direction and 0 in the y direction. Looks like there's a place here where both slopes are 0. Go back to the derivatives. Yeah, if I made x equal to 0 and y is equal to 0, this slope would be 0 and this slope would be 0. So it's the only place where both slopes are 0, and I see that. This, what I'm going to call later a saddle point. All right, so taking the derivatives, one of the main things I want to say with this example is, with this notation, the final answer is a number, whereas with this notation, just f sub x, the final answer is a formula. All right. These derivatives are rates of change. We've seen them as slopes on a 3D graph. Let's do an actual example to sort of get some idea of what they mean practically. How is this good? How is this useful for us in real life? Well, here's a function. Now, it's a function that gives you the future value of $1, n years with n compounding periods. So the future value of $1 in 10 years, compounding periods. So if you get interest once a year, then there's one compounding period per year. If you get interest twice a year, if it's like semi-annual interest, then n is equal to 2. Sometimes you have daily interest savings accounts, so you get it every day, so n is equal to 365. Could be quarterly, 4 times a year, so n would be 4. And r is the interest rate that you're getting, the annual interest rate that you're getting on your dollar. So this function's output is what a dollar will be worth 10 years from now with interest rate r and n compounding periods. Okay, that's what it means. I want the two derivatives. So I'm looking for f sub n. So I need to take the derivative of this function with respect to n, r being a constant. Well, my hesitation there is, this looks like it's going to be hard, right? Because there's like an n down here and an n in the exponent. The derivative with respect to r is going to be so much easier. All right, but we still got to do the n. I'm going to use the idea of logarithmic differentiation. So this f is equal to, I'm going to take the ln of both sides, because when I take the ln of this, the 10n comes down out front. So I think it's going to make my math easier. Yeah, because now when I differentiate, I'm differentiating with respect to n. So and r is a constant, so that's like implicit differentiation here. That's going to be derivative of ln f is 1 over f times the derivative of f with respect to n, okay, is equal to, so I differentiated this side, now I got to differentiate the right-hand side. So product rule, derivative of the first, leave the second alone. Leave the 10n alone. Now I'm differentiating this piece. So that's going to be 1 over 1 plus 1 times the derivative of what's inside. What's the derivative of this piece with respect to n? So that's r n to the minus 1. So the minus comes down, subtract 1 from the exponent. All right, so took the ln of both sides, so I made my derivative easier. It was kind of easier, but I mean, it still makes an ugly formula. But I get to solve for f of n. So for solving for f of n, all I got to do is multiply the f up to that side. So f of n is equal to f times this whole thing. Oh, and what's f? That's f. So here's the derivative of that future value of $1 with respect to the number of compounding periods. The formula does simplify up a little bit. You can clean this up a little bit. Like this n and this n can cancel, but let's just leave it like that for now, because we still got to do the other one, right? The derivative of f with respect to r. So now I'm differentiating with respect to r. This one, I don't think I have to do logarithmic differentiation, because that would be like n is a constant. So if it was like brackets squared, the 2 would come down, subtract 1 from the exponent. It's 10n, so the constant comes down, subtract 1 from the exponent, and now times by the derivative of what's inside. The derivative of what's inside is just 1 over n. Remember, n is a constant. I'm differentiating with respect to r. This one cleans up. That n and that n cancel. In fact, let's just do that because it's here. The first derivative that we made, the first partial derivative that we made, also cancels, but this cancels so nicely that let's just do it. All right, so I've got the two first order partial derivatives. What do they mean? Interpret the two first order partial derivatives. Well, we could talk about it geometrically as some kind of slope. But I want to talk about, it's a money formula. Let's talk about it in terms of money. And to make it more real, let's give an interest rate. So I'm going to say that, say the interest rate was 3%, and say compounding period was 4. So this investment that we're looking at, that we're putting our dollar in, and it's going to sit there for 10 years, I'm going to get 3% interest compounded quarterly. Let's just figure out how much is that going to be? All right. Our future value of our dollar, this would be 0.03, and this would be 40. So in this investment, evaluate numerically, every dollar I put in, wait 10 years, I get $1.34.83, $1.35 almost. Okay, so I put $100 in, I'd have $134.83, for example. But maybe I'm in the bank and I want to negotiate something, right? If I could get a higher interest rate, then that would, make me more money in 10 years. Or if you could compound things more, that would also increase the amount of money. So what should I argue for? A little bump in interest or a little bump in the number of compounding periods? Well, I have these partial derivatives here. That's what the interpretation is financially. So this derivative with respect to n means if I could increase the number of compounding periods, how much would the value of my dollar, future value of my dollar, go up? So I'm going to take this expression and plug in, so take this expression, and I'm going to get numbers for them now. Everywhere there's an R, I'm going to put a 0.03. Everywhere there's an N, I'm going to put a 4, because I want to get the slope at that point. Well, I got to go smaller here so we could see it. even smaller so we could see it. I'll make the thing bigger in a second. To have everything subbed in, yeah. So now this is the slope of the curve in the n direction. Small. What about the slope of the curve in the r direction? Well, same thing. I've got the slope formula. Let's just, everywhere there's an n, put a 4. 40 minus 1, that's to the power 39. This one's easier to plug in. And, oh, quite a bit bigger. So increasing, although common sense would have said this as well, increasing the interest rate by a little bit gives me more money. The slope is 13. So I should fight harder to increase the interest rate in my deal more than increasing the compounding period. The compounding period really doesn't do much. It increases it, it's a positive slope. So if the guy says, you want 5 or 4, take the bigger one, but it doesn't make that much of a difference. We've seen functions of more than 2 variables. So here's a function of 3 variables. So it's a 4-dimensional function. The input is, the domain comes from R3. We can see that the domain, since we're allowed to take the arctan of any number, so the domain is all of R3. Anyway, the point of this example is we can have derivatives with respect to any of the independent variables. So here I'm differentiating this function with respect to x. So the 2 comes down, subtract 1 from the exponent, the y and the z are constant, so the y to the 5th times z is a constant. Derivative with respect to x, the 2y is a constant, and here arctan of z is a constant with respect to x, so its derivative is 0. That was not too bad. The derivative with respect to y, well, same idea, but now the x is a constant and the z is a constant. So I'm just differentiating with respect to y. 5 comes down, subtract 1 from the exponent, differentiate with respect to y, and again the arctan of z, derivative is 0. Lastly, our derivative with respect to z. So finally we're going to get to do something with that arctan. So I'm taking the derivative of everything here. X is a constant. I'm differentiating with respect to z. So x is a constant, y is a constant. So our derivative, there's no z in that, so it's a constant. And arctan, finally we get to do something. The derivative of arctan is 1 over 1 plus z squared. So it has 3 first-order partials because it's a function of 3 variables. They have the same meaning, but I can't sketch it and draw it. This next example has our second derivatives in it, finally. So we haven't done any second derivatives here. So let's get all these derivatives here. So I need all these derivatives. So I'm getting ready here. Nope. So this is a function of x and y. So it has two first order partials. You can either differentiate with respect to x or differentiate with respect to y. Those are my two choices. So let's do them. So here I'm going to differentiate this function with respect to x. So y is a constant. 2 comes down, subtract 1 from the exponent. Differentiating with respect to x, so 2y is a constant. Derivative of ln y, ln x, 1 over x. All right, not too bad. There's my derivative with respect to x, the slope formula in the x direction. Let's do now with respect to y. So x was a constant, so x squared I just left alone. Now I'm differentiating with respect to y. Oh, there's no y's in here, so its derivative is 0. Now I've got my two first order partials. Now let's get our second order partials. So that means I'm going to be differentiating twice. So that's why there's 4 choices here, because you can go x, xy, yx. There's 4 different versions of the second order partial. So taking the second derivative is just take the derivative of the derivative. So mechanically, it's not too bad. We've already got this derivative with respect to x. So I'm going to differentiate it again with respect to x. So 2 is a constant, y to the 5 is a constant. There's our derivative. There's no x's in here, so its derivative is 0. I'm seeing this as x to the minus 1. So I'm seeing this as x to the minus 1. So the minus comes down, makes that a plus, and subtract 1 from the exponent. And you could write this as 1 over x squared, or I could just leave it. So there's our second order homogeneous partial. Homogeneous, they're the same, y. Let's do the other homogeneous second order partial, y. I have the derivative with respect to y. I need to just differentiate that with respect to y again. 4 comes down, subtract 1 from the exponent. There is no y's in here, so its derivative is 0. Okay, so there's our two homogeneous second order partials. We have two heterogeneous second order partials. So differentiate with respect to x, then differentiate with respect to y. So differentiate with respect to x, done. Now I need to differentiate this with respect to y. So x is a constant. The 5 comes down, that's a 10. Subtract 1 from the exponent. I'm differentiating with respect to y, so this becomes a 2, and there's no y's in there, 0. So there's our heterogeneous second order partial. The next one, I differentiated with respect to y first, got this, and I need to just differentiate it now with respect to x. So the 2 comes down, makes that a 10, subtract 1 from the exponent, y to the 4th is a constant, the derivative of 2x with respect to x, there. Oh, note to self. X, the derivative with respect to x and then y is the exact same as the derivative of y with respect to x. These are the same. So I said there was 4 second order partials. There are, but 2 of them are the same. That's always true. In fact, let's skip down here. We'll do this example in a second, but that's what this Clairaut theorem is all about. It's written in math lingo. Suppose f is defined as, on a disk that contains the point a, b. The functions f of xy and f of yx are both continuous on D. Then this just says the two heterogeneous second order partials are equal. That's what we found in our example, that they were equal. Clairaut's theorem says that's always going to be true if f of x is a continuous function at that point that we're evaluating at the point that we're talking about that second order partials. So most of the time we are, except for weird functions. So Clairaut's theorem, the two second order heterogeneous partials are the same. In fact, we can even expand upon Clairaut's theorem. And this is, it doesn't matter what order I take the derivatives of it. That's 1, 2, 3, 4, that's 4 x's and 2 y's. As long as I have 4 x's as derivatives, x, 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 and 2 y's, they're the same, assuming that f is a continuous function. So it doesn't matter the order, just how you differentiate it. Now, once you understand that concept, or accept that concept, and because we haven't proven Clairaut's theorem, it's hard to prove Clairaut's theorem, we haven't proven it yet. We've shown an example of it. If you were to practice, do some homework, do some partial derivatives, every time you did a second order heterogeneous partial, you'd get the same thing whether you did x first and then y, or y first and then x. You would see that that happens. And then you'll accept it to be true and potentially forget the name Clairaut's theorem. And you might think, well, yeah, why do I care what the theorem is? I understand what it means. You should think about, or I would advise you to have the term Clairaut's theorem also memorized, because whenever it shows up and someone says, why are these the same? If you don't know the word Clairaut's theorem, the term Clairaut's theorem, the name of the theorem, then your answer to why are these the same is some sort of a long, rambling explanation, whereas the alternative is you just grunt Clairaut's theorem. So you look like you really know what you're doing if you have the right terminology. I would recommend Clairaut's theorem. When you take differential equations and you're doing exact equations section, we're going to use this property, and a lot of times it's not named, but you'll get to put your hand up in class and, isn't that Clairaut's theorem? And everyone will think you're a genius. So Clairaut's theorem, it's a good thing to know. Anyway, let's do this one last example. What's about this one last example? I'm looking for f sub x, but all the letters are mixed up in here. So I'm going to make my note to self here. Z is a function of x and y, but it's an implicitly defined function. Well, I'm going to differentiate. I'm going to differentiate using implicit differentiation. So I'm going to take the derivative of this side. Product rule, because x is a function, and I'm differentiating with respect to x. Y is a constant, since I'm differentiating with respect to x. Let's make this z sub x. Same thing, changing notation is going to make it a little bit more clearer. All right, product rule. X times sine z. Derivative of the first, 1, times leave the second alone, plus leave the first alone. Now I'm differentiating sine z. That's cosine z times the derivative of what's inside. What's the derivative of z with respect to x? That's my z sub x. So now I've differentiated this left-hand side. Let's differentiate this side with respect to x. So y is a constant. So here it's just going to be the 2 comes down. Oh, wait, before we go nuts here. This is a function of x, but z is also a function of x. So I got to do product rule on this again. Let me throw brackets around this. That's a function of x, and z is a function of x. So I'm going to have to do product rule on this. So derivative of the first, leave the second alone, leave the z alone, plus leave the first alone, times the derivative of z with respect to x. So this is our implicit differentiation. So that's, this part is product rule on this part. All right, now I got to differentiate. This one's more straightforward because it's just differentiating with respect to x. Y is a constant. And here's another chain rule. The derivative of arctan z, that's going to be 1 over 1 plus z squared times z sub x, implicit differentiation. All right, I'm not done yet. I've differentiated all of this. I got to solve for z sub x. Okay, everything with a z sub x I'm going to put on this side. So I want this to go over here, so it becomes a minus. I want this to come over here, so it becomes a plus. That doesn't have a z sub x, so I'm going to bring it over here, and it's going to become a minus. All right, every piece here has a z sub x on it, so I'm going to factor out a z sub x. Now all I got to do is divide this big bracket out to the other side. So z sub x, so I'm going to divide both sides. Let's put this, zip, boom. There's my formula. I've solved for z sub x, the slope. Implicit differentiation. Now this formula has z's in it. Yeah, the original function was implicitly defined, so that's as good as we can do. So now partial derivatives. It's just a lot of practice and remembering your old single variable calculus differentiation rules, right? Like arctan and arcsine and all of those things are maybe not top of mind. But with some practice, they'll come back.